Hey class, this is Mr. Schmidt for our December 4th lesson on conservation of energy. So the idea of conservation of energy is once you put work into a system, remember work is the change in energy. Once we put work into a system, that energy will stay within that system, okay? So we have to be careful about what we define as a system. But once it's there, all that energy is going to stay, and it can change forms from one to another as it moves different states. But we should be able to account for all the energy and go through its process here, okay? So if 100% of the energy is in potential, as you go halfway down, half of the potential has been lost and is now kinetic. If you go 100% of the way down, it is now 100% kinetic energy and zero potential. And you can have any mix therein as the object moves up and down. So what we're trying to do is do a computational model to calculate the change in energy and be able to calculate energy. So I started with asking you, how much energy does gravity do on the car? And there's going to be two ways to solve that. So let's take a look. Okay, so as we look at this, we see that gravity is pulling down, right? Okay, and our displacement is moving in this direction. Okay, and that was 0.5 meters. So we can solve this a number of different ways. The one way is our force times our distance times the cosine of theta. But we have to be very careful at which angle we want to use. So I prefer to take this and just make sure that the force and distance are parallel to each other. So if this is our setup, remember what we could do is we could break this up into our force in the X and our force in the Y. Okay, so this is going in the X direction, this is going in the X direction. So we're going to have two things that are parallel to each other. Okay, so now we just need to know what our force of X is. Okay, and if this is my theta, then I can do times the sine of theta. Okay, so my force of gravity is going to be mg. Okay, so my m was 0.5, g is 9.8, theta was 30 degrees. Okay, so we get 0.49 joules equals our work. Okay. Now, if we come back to our screen here, we see the exact same setup, only now we're looking at the potential energy of the car. So how do we go through this with the car? We're going to have a similar setup here. Okay, so we have the similar setup, only now we're going to use potential energy. Okay, so I call it PE. Some of the equations are going to call it U. Okay, so this is the potential energy due to gravity. So we know what M is, we know what G is. Now we just need to find H. Okay. So, and this still was our okay, so now we can plug these numbers back in. Now, we didn't actually have to do this because work is the change in energy. So by no coincidence here, we get the exact same answer. Okay, which means our next question is going to be even easier because now we can start applying this. So if the question is, how much energy does how much kinetic energy does the cart have at the bottom of the ramp, then we can look and see this. Okay, and we don't really have to do any math. So if we come back and look at the paper, now if we're down here with the cart, okay, it's still, okay, we're going to be at 0 meters. Okay, so all this work went into potential. All that potential went into kinetic. So now my kinetic energy at the bottom is going to be the same number. Okay, so you'll often hear the phrase a joule is a joule is a joule, because we can conserve energy across any system or any point within the system here. Okay, so now if we took that number and we're looking for the speed at the bottom of the ramp, or the velocity at the bottom of the ramp, then we can come back over to the paper and we can use that K equals 1/2 mv squared. Okay, and we had our 0.49 joules equals 1/2 0.2 kilograms times v squared. So we're going to divide both sides by 1/2 times 0.2. Okay, we're going to take the square root of all of that. All right, and if I look up my calculator, I got 2.21. Okay, so that is my speed and velocity at the bottom of the ramp. Okay, so that answers the question of velocity at the bottom of the ramp. All right, and then all that goes into supporting the idea that energy can be neither created nor destroyed. It can only change forms. Okay, we could add to that, matter and energy can neither be created nor destroyed. They can only change forms, so that when we eventually touch on the nuclear physics and modern physics, we can account for things like Einstein's theories and others who've expanded on all the different variations here. Okay, all right, so the idea is all the initial conditions are going to be put on one side, and all the final conditions will be put in over here. Notice we're not going to talk about the force of friction. This is going to be the energy lost due to friction. And that energy normally appears as heat or sound, okay? Okay, so if we're looking at the questions for the in-class work, we can use that as a model to go over other examples that we'll build on later. So if we are looking at different points along this slide, we can say the energy here has to equal the energy here, has to equal the energy here, okay? So that means my potential energy plus my kinetic energy plus whatever work I put into it, plus anything else we can keep adding to this has to equal the same thing here. Okay, so we can start adding in new elements here like heat. Okay, we could add in sound, we can add in light, we can add in whatever we want to for any of these intervals along the way. Okay, so if we were looking at the energy loss due to friction, okay, remember it's not lost, it cannot be created nor destroyed, but it could change forms. Okay, so we could do, the force of friction times the distance, as long as they're in the same direction. And friction always opposes displacement. So as long as we're using this displacement, we should be able to be fine with that, okay? So that's how we could do this, because this is going to be equal to the work done by friction. Okay, so that's where we could take that and we could put that in there as well. Okay. Okay, so maybe there's two components here. Maybe this is the heat. Okay, so in which case we would not list it twice. Okay, all right, but there's going to be heat, there's going to be sound, there's going to be light, there's all sorts of things that come off in the forms of different forms of radiation that if it's not contained from within this system, then it's not accounted for. So we need to account for everything going forward, okay, because energy can change forms and it can leave a system, but it cannot be created or destroyed. Okay, so hopefully that gives you a nice start, ends you off on the week. And we'll see all of you next week as we go further into conservation of energy.